So next thing that I would like to explain to you are my favorite BUPUs, which are the bounded uniform partitions of unity. So roughly speaking, it's a good way to localize a function by cutting it into little pieces. And if you think of Riemannian integration, then you decompose a continuous function into blocks. That would be the most primitive way of cutting everything into pieces. But if you want to do this in a more smooth way, then you have to be more careful. But this is easy to explain using Fourier transform methods. That's why I'm doing it here now. So I start with a command which is I'm probably just doing it once more. This you will see much more of these guys here, but to give you an idea of what a bounded uniform partition of unity is, I first display one of these elements. Okay, so the BUPUs are, again, B is bounded. Boundedness means with respect to some norms, you might say, well, they're all equally, I don't know, smooth or so, but in my case, they are just shifted versions of one particular function, so I don't have to worry about it. The U stands for uniform size, so all of these bump functions have the same size because they're just shifted versions. And I'm moving along, I have signal length n, and I'm moving along the lattice constant a. That's our standard with 480 and 20. And now the thing that I would like to show first is the general case. So if I will explain how to do this later on, but if you're supposed to get a collection of points, so the XP, maybe I should explain this also, is a sequence of coordinates which is, I've chosen coordinates by some random process at positions 1, 3, 26, and so on. You see it's quite wildly varying or so. And I think I was just using it was a random number generator uniformly between 0 and 1, and I choose the ones which are bigger, so the top 10%. So roughly speaking, you will see that maybe I'm also showing you the LXP. So how many points do we have? We got in this experiment, we got 50 points. Yeah, you see that's about 10% of 480, 448. So it's a random process. Okay, fine. And so what I'm doing here is I'm first of all producing the collection of all these shifted functions. So when I used my command translation basis with a sequence of indices, and I will plot this for you. And remember, I'm a guy who prefers to have row vectors. Therefore, I have, for the plotting routine, unfortunately, I have to do it by transpose. Everything is real valued, and you see it's quite accumulating here, also to the right, and it's quite sparse in this concrete case at 200 or so. And therefore, if I take the sum, now the sum in MATLAB is taking the sum of a collection of vectors. I have here a 50 by 480 matrix in the sense of column-wise. So I'm adding up all these functions, and you see the sum is a ragged function. It's quite small, near 0. Actually, it's going down almost to 0, but not really. Because I'm choosing Gauss functions, so even in the discrete setting, they have fairly big support, but with small values far away from the center. Now the idea is that for each of the entries, from this collection of 50 shifted Gauss functions, I divide by this sum, or I divide through this. And then, of course, if I say, well, what is the sum of these things? It's the sum of all the Gauss functions divided by the sum, which is constant 1. So it's a simple way to produce a partition of unity. And you see, this is a kind of strange partition of unity because it has different expressions, but in in uh, in the areas where you have few elements, the contributions are big. There, in the areas where you have big collection, they're getting small. And the point is, since each of these guys is multiplying this original bump function by another one, by a continuous function, which is bounded below by 0.03, this will be a collection of continuous function, which is the most general case, a so-called irregular bounded uniform partition of unity. Actually, when you go to 2D, the same trick can be observed. So in this case, I mean, instead of summing up, I would say I'm doing a convolution of my indicator function where I put a 1 at all the sampling points. So I could say, yeah, maybe I demonstrate this here. I could say put XPO is indicate Dirac comb, now an irregular Dirac comb, but I put XPO at XP equal to 1. And then I could say as conv, the summation via conv is IFFT of FFT of this Dirac comb. And you know every single unit vector gives a shift, and therefore this should work fine. And the original element that I was shifting around here was the BSP, so it's a B-spline. It's a compactly supported function. Now, sorry, I have to convolve, means I'm multiplying the Fourier transforms on both sides, and I do the inverse Fourier transform. Now, from the plot, you see that this is supposed to be real valued, and I know it should be real valued, so the imaginary part, which will be close to 0, can be eliminated here. And then I would like to check whether this as conv is the same that we have here. So comp norm as BUP2 and as conv. You see it's a bit risky that I'm changing the code here while you're looking at the presentation, but let's see how it works. So first, I'm just repeating this now. This sconf has been created. And now I'm creating this, and yes, it's the same. So in the point that I wanted to make is, if you're giving me a partition of unity in 2D, it's fairly hard to create, because I mean, in 1D, you just take the indicator functions that you get from a Riemannian sum picture, and then you smooth them out. But in 2D, you would have to define Voronoi domains and all these things. And in this case, I found out that this trick of choosing 2D Gauss functions, moving them around, creating with a two-dimensional Fourier transform what I have called this sconf, this sum created by convolution, and then creating by division the partition of unity is a good way to do it. Okay, so this is another situation where I was creating in a similar way a partition of unity, which was, I think in this case, I tried to keep a minimal, that's a different, I mean, another way to create such BUPUs. If you're doing it with a random number generator, you're very likely to have some small cluster and some big gap with high probability. If you want to avoid this and say, I wouldn't have to have either, then you can say I make a progressive sum. So you say I'm moving at least a minimal distance of 5 pixels or so, and a maximal distance of 15 pixels. That means you're choosing first the distances in the 1D setting, and then you're taking a cumulative sum to create the indication. So the sequence XP can be created in many different ways. Now, let me see. Yeah, I think this other than BUPU is exactly done in this way, and I just show you the key part of the thing. So again, I'm creating some building block, my phi. Maybe I'm showing this to you as well. So plot C the phi, and maybe a figure, and also yeah, maybe I should just show this to you. So you see, it looks a little bit like an approximation to the Gauss function, but it has been obtained by taking a rectangular filter with a distance of 15. So you could say I'm taking lattice constant 15 means a rectangular box function with 7 to the left, 7 to the right, and 0. So filter symmetric and 7 would give this, but smoothed with a base. It was a rectangular function of size 5, and you smoothed 4 times. So it has been convolved 4 times. So this is a function which, if I would do it in a continuous setting, would be 3 times continuously differentiable. Or maybe even 4 times. Yeah, I think that would be correct. If I would choose here only instead of 4 a 1, you would just see a trapezoidal function which is continuous but not differentiable, and so on. So now in order to create this situation, and you see it's more regular but still somehow irregular, and here I have marked the positions. So I just want to show you how I did this. I was saying the step which, so the ascending or whatever, minimal step which is more or less 7, and then I'm doing a round command, so with low probability it will be 0 or 8, but with slightly higher it will be 1, 2, 3, 4, 5, 6, 7. And then I took the cumulative sum, which of course exceeds my signal length n. Therefore I have this nice command in line number 15. I cut off all these elements in the cumulative sum which are beyond n, so I leave only those coordinates which are less than this. Maybe now I can display it and you see how it runs. So you have a sequence, and then maybe also I'm putting the length of this, so the number of shifted functions that I will use. Now a new experiment. Okay, no, it's not length. It should be length of xp, of course. How many coordinates did I choose? And you get 42 in this particular case. And then I'm creating the collection of translations, and I do the same thing that I have been doing before. And you see, I don't know, maybe I should choose the other plotting routine with density 1, and then run it once more, and then we were done with this experiment. So you see they are a bit more faint, but clearly at the areas where I have small step width or higher overlapping, the amplitudes will be decreasing. It's, of course, it looks as if they were all shifted and scaled versions of one bump function, but no, it has been divided by sum, but the sum is, of course, a linear combination of those original shifted elements. So it's very smooth, and they are very narrow, so you don't see a big difference. Now, I'm not sure. Yeah, okay. Now I'm telling you a little bit more about these B-splines. So the idea of splines is they are more flexible than ordinary polynomials. So when somebody wants to interpolate data, and you would try it with polynomials, let's say 20 data points, you have to choose a polynomial with 20 coefficients. So you could use the fundamental matrix or so. Then you would get a typically very crazy polynomial which exactly goes to the correct values, but otherwise in between it's oscillating terribly. If you would change your value a little bit, you would get a completely different one. So that means the fundament matrix, which is responsible for the creation of the coefficients of the interpolating polynomial, they are quite badly conditioned. Therefore, it will not work well. So what I'm doing next is to show you maybe first the plot, the B-splines of order 0, 1, 2, and 3. Now the order is the number of coefficients, and clearly you normally describe polynomials in terms of degree. So if I say the number 3 is the B-spline which you get by using cubic polynomials or so then you would say that if you would do this in a continuous setting, that you're getting functions which are convolution product of order 4, so 4 times a guy like this, and I will demonstrate it separately or so. If you convolve it only once, you're getting this here. If you're convolving 2 times, you're getting this here. You're convolving 3 times, you're getting this here. Now, the cubic splines, which have 4 coefficients in the description, they are C2, so they have continuous curvature. That means if you're doing a linear combination of this, maybe I should, maybe that's a good example. If you take a linear combination of shifted cubic splines, you get such a curve. Now, what does it mean that this second derivative is still continuous? My usual way of explaining it is the following. Assume that you would have a road going up the mountain like this. Then you have no sudden change of curvature. So if you're driving along this road, the curvature is related to how you drive. So if you the angle of your the radius of your car driving around the curve depends continuously on your position. So that's kind of a smooth way. It's not like a toy train where you would have a change from straight to fixed curvature. And if you would drive that, you would say, suddenly I'm having my steering wheel would go from this position to this position, which corresponds to the radius. So that's why cubic splines are very, very, very nice or so. Now I will maybe insert something here. And it's the following. I would say maybe I'm saying box 10 is filled symmetric n and 10, and then I would say maybe I take convolution power 4, and then I'm saying the element generating these cubic splines is, well, I'm doing convolution several times, so I know it will be real, so I put the real in front, IFFT of FFT, and instead of taking the convolution by product, I just say a pointwise product of this. So if you want to see now what's happening or what's going on here, the BUP, we look at the whole scenery from the point of view of Fourier transforms. And the picture should not be surprising to you, because the first one is showing you the rectangular function with the Fourier transform being the sinc function. Now, if you look at the sinc function and you take the force power here, then you see something like this. Maybe I make it now a little bit stronger. Default plot 2 makes the line mode a little bit stronger or so. But meanwhile, I think I would like to show you. Let's take the convolution square first of all. So I'm running this. Then you will see a little bit better what is happening. So again, the box function, having this here. And now square of this function, clearly this is a real valued function, will be a non-negative function. Also the decay is like 1 over x, that will be like 1 over x squared. So it's already visible, it's a little bit above the line. You could zoom in and look at details or so, but what you're getting here is the triangular function or so. Now I'm just saying that take um, uh, the probability distribution. That's kind of, we know that convolution in the discrete setting is like multiplication of polynomials. So if I would say, now let me see, polynomial, yeah, okay. If I look at the experiment with the dice, and I take the MATLAB convention of decreasing polynomial, then I would describe the corresponding polynomial, meaning as x to the 6th power. Okay, so I should say, of course, the dice is a probability measure, so the amplitudes are equal, but each of them is 1 over 6, plus x to the 5th, and so on. Yeah, and going down to x to the power 1, and the whole thing divided by 6. So that would be a polynomial encoding the probability from one dice. But maybe I leave it out for two. It's more visible. Now, what is the product if you take two dices? So I'm convolving the dice with the dice. Oh, sorry. And you see certain probabilities. So if you want to know the probabilities, of course, the factor 1 over 6 has to come twice. So what is the probability of getting, and now you have to read it backwards, a 0? Never. A 1? Never. What is the probability of getting a 2? And you all know it's a 2 is a poor outcome of your experiment. It's 1 and 1. So it's 1 over 36. What is the probability of getting a 12? 12 is the highest degree, so it's the position 13. And the probability is, of course, very lucky guy, 6 and 6 is 1 over 36. What is the probability of getting a 7 if you count properly? It's 6 over 36, which is 1 over 6. So the probability with two independent dices to gain 7 is the same as, let's say, to get a 3 or a 5 from one dice or so. So this is a distribution that you can get. And you can also visualize it in a different way. You can say RD is a random matrix, 1 and I don't know, 100,000. MATLAB is very, no, not 1. Yeah, okay, let's do it. RD2 is a random 2 and 10,000. I shouldn't display it. Well, it's even, well, whatever it is, yeah. Now let's look at figure. Subplot 1 to 1. I would like to see a histogram of RD, and then subplot 1 to 2. So I'm cutting in the horizontal direction, and I want to see a histogram of RD, no, of the sum of RD2. So I'm in the first case, I have a uniform random number generator, and in the second case, I'm taking the sum of two random variables, and you see it's what you expect. Maybe I should make the bins a little bit smaller, yeah, more narrow, maybe 30, so that's a bit too much, 30, and here I'm taking histogram, maybe even with 50. Let's see if it works. So it's a repeated argument. Yeah, okay, it's very nice. So you see, maybe I should multiply this number to make a better impression. The uniform number generator is quite fine. It gives almost constant probability. The bins are of this discrete measure are fine, but also the sum of two of them is like this. So if I would now say what is yeah, I mean, I think, yeah, well, maybe let's do it. What is the histogram? So figure once more. Histogram of the sum of a random variable, now maybe with 10 and something very big, and histogram should be with, let's say again, 50 bins. I would like to leave it here. Then you see it's already very nice, and you smell that we're approaching the central limit theorem, so this will be close to a Gauss function, but this is a little bit deviating from it. So the point is, the B-splines are coming from these convolution squares, and as you have seen here in the beginning, I think this, no, in the yeah, here. What I'm doing here is I'm choosing the overall signal length. I have to tell MATLAB what I need, what kind of functions I need, lengths. Then they should produce a partition of unity if I take the rectangular guys. So A has to be a divisor. And then I have to say how many times do I have to convolve, and because it's sometimes useful to convolve with something more narrow, I do this here. I'm not changing, leaving the A here, so that's the standard. Cubic splines would correspond to BUPU spline N, A, and 3, because I'm doing 3 times a convolution. Now, the so-called, I mean, how can we use splines or so? And there are two different ways, and the first one is the simple and easy one. It's what's called quasi-interpolation operator. So let me see. Yeah, so the quasi, I have to explain this plot in more detail now. So again, you see I'm choosing from 0, 1, 2, 3. So I have no, I shouldn't use a MATLAB index running 0. So it should, the MATLAB index goes from 1 to 4, but I'm doing the convolution either not at all, which means 0, which means rectangular function, using j equal 2 means j minus 1 is 1. That means I'm taking triangular function and so on. So I'm doing 4 things. So and then what I'm doing here is I'm creating this partition of unity. This is the collection of shifted functions which add up to 1. But then I choose from my nice function. Okay, I should, yeah, here's this nice function. I choose the sampling values, and I take as much of the partition of unity as I would get here. So where do we see the, you see the sampling values of the yeah, the black function is actually plotted. So you see here the black function, it is sampled at certain positions. Now the first guy here is the rectangular interpolation. So I have been choosing a rectangular function which is symmetric, and that's where you see that you have a step function. So it's very easy to do, and of course you can do it also with a convolution, because there's a sum of shifted things where you first more or less multiply. Maybe we should also demonstrate it here. You could say, instead of sampling and using the values for linear combinations, kind of in this linear algebra sense, linear algebra component, I could say, no, I'm multiplying the original smooth function with sampling values with the Dirac comp, so that this would be a sum of unit vectors, and then I convolve with the elementary with this B-spline with the element. But in both cases, you would see the same plot, of course, and to get the same result. Now, what would be the next one if you go from constant to order 1, order 2? So 2 degrees of freedom means piecewise linear. It's not so well visible. Maybe you look at the more exposed points like here. You see it's a piecewise triangular, this light brown. It's a piecewise linear interpolation. So it's going up and down, connecting now my red stars in a decent way. Now, why is it called quasi-interpolation, or it's in effect approximation operator? Well, this is because the next level, the quadratic splines, and especially the green ones are the cubic splines. They are quite nice. So they try to follow this curve, but they are not interpolating anymore. So that's one of the drawbacks of this spline function. So here you see again the things. This is just another example where you see that maybe if you're sampling too coarsely, in this example, very much you see how much you can cut off, independent of whether you're taking a smooth interpolation or this. So why is this or where is this a problem? Well, the black guy here is a smooth function, but it allows to have too much oscillation, which are beyond the sampling width and the smoothness of the bump function. So remember, if our bump functions are looking like this, it's clearly very difficult to represent a function which has peaks and bumps which are more narrow than this. So it's close to impossible. So you can talk about how to get the best approximation. That's actually not necessarily the best approximation. That's a different story, which I will try to explain next. And yeah, the other thing, which this is a quick illustration, it's the same story, and I had forgotten my experiment, and now I saw it and said, what strange picture, but no, it's just showing you these approximations. So these 4 different quasi-interpolating things, but now at the spectral level, which means you look at the Fourier transform. And you can imagine that probably here I was taking a smooth function, maybe even a band-limited function. So the cubic spline has a lot of concentration, whereas the step function, clearly you need a lot of high frequencies to represent the step function. That's why the spectrum is very nasty. It's a little bit better, but still there are spurious contributions outside, even visible contributions outside here for piecewise linear. Quadratic is already better, and cubic you cannot see much due to the thickness of the line, but you could also zoom in and you would have a very good approximation. So the moral should be that if your function is extremely smooth, if you're doing a cubic spline quasi-interpolation approximation, or if you do best approximation, then you're having a good approximation. Let me see. Yeah, well, I think I will interrupt the recording now and start a new one in a moment.